Hi, good day. My name is Diana, and today I would like to talk about the implementation and calibration of a low-cost propeller type current meter in a laboratory. So this is the outline of my presentation today. So first, I will talk briefly about the introduction. Second, the implementation of propeller type current meter, which is I separated into 4 segments, and then the calibration, result and discussion, conclusion, and last but not least, references. So for the introduction, I'm start with Tumansky 2006. Flow velocity measurement, also commonly used in the industrial sector, such as food and beverage, petroleum, chemical, and many other industries, to measure velocity of various gases and fluids. Velocity area are mostly deployed in stream and such meter, such as current meter, acoustic Doppler device, and floats. Current meter are divided into groups based on the orientation of the axis of the rotor, and the horizontal axis rotor meter are referred to propeller type current meter. The advantage of horizontal axis current meter is not easily to become tangled in the debris and grass of flowing river. Propeller type current meter or horizontal axis rotometer is an equipment that is used to estimate flow velocity in various fluids such as air, water, and oil. Several standard propeller type current meters has been produced by company all to cater the demand, but these products are costly and limited in accuracy of real time during data recording. The design and the implementation of proposed propeller type current meter is for river and stream application, and thus a velocity area method was used. So for the second part, the implementation of propeller type current meter, for the first section, construction of the mechanical component. As we know that the current meter determines the water velocity using mechanical means. The velocity of water forces the rotor to evolve at the same speed as the flowing river. The linear equation is used to estimate the water velocity by relating it to the rotation frequency, or the number of revolutions produced by the rotor. The number of rotations produced by rotor is then counted in each period of time. Figure 1 shows the process of making the prototype of propeller type current meter. A. The lathe machine was used to craft the juncture wood 2 cm by 3 into a dome shape known as spinner nose cone. Sandpaper was used to smooth the spinner all out after shaping so that it lifted over the propeller hub. It fitted the propeller hub, and the worm screw shaft was screwed into the spinner that attached together with the propeller hub. The spinner made the water current more streamlined. It reduced aerodynamic drag and smoothed the water flow so that the propeller entered the water intake more efficiently. The design of the propeller or blade must be symmetrical with respect to the code. For time and cost reduction, computer vane propeller was used as a blade. In construction of meter electronic, I manipulate ATmega 256 ohm microcontroller board because it is easy to adapt in any design and low cost. The board have digital input and also analog as well as analog digital converter ADC. The board also supported different bus protocols such as I2C, SPI, and TTL. This makes the microcontroller board capable to manage the RTC module the CD modules, and the transducer module correspondingly by using this bus protocol. The specific of transducer used in the meter is depicted in the table 1. The inductive proximity sensor is used to separate various metallic materials on the basis of the amount of current produced due to the change in the magnetic field of the sensor. And the variable in current is directly proportional to the distance of the metallic materials from the sensor. So this proximity sensor provides medium or low resolution sensing depend on the number of pulses measured per volume. So a cooper rotates with the impeller at every full rotation. The induce a pulse by using electromagnetic in the waterproof coil, which is proportional to the water current speed. And these pulses were counted by the microcontroller. So for the programming part, the program was divided into 4 procedures: the initialization, measurement, recording, and transmission shown in figure 2A. In figure 2B shows the process of counting pulses performed by the microcontroller. In figure 3A shows that the cooper rotates with the impeller, and every full rotation it induces a pulse by using an electromagnetic in the waterproof coil. The conditional circuit uses 1 k ohm and 510 ohm resistor as a voltage divider. This output pulse produces a low signal at 0.1 volt and 4.98 volt for typically high signal shown in B. Whereas for C, so for every 1 second, these pulses are counted by the microcontroller, which is proportional to the water velocity in meter per second. For calibration part, the flow channel was used to perform calibration of current meter. It is a self-contained open channel designed for studying a flow phenomena. The current meter is fixed in a particular place or spot in the channel and let the flowing water move the propeller. Pulses produced by the meter are counted and recorded its rotational velocity. And the standard meter used in the calibration process was a Nixon string flow 430 flow meter. The prototype current meter and the standard current meter receive the same amount of velocity. During the process, the magnitude of velocity is not important. However, the flow velocity supplied by the flow channel to both meters must be maintained and stable. Thus, the value displayed in the test meter is compared with the standard meter. The cost of proposed propeller type current meter is summarized in table 2 because we are enter the result in discussion section. We show an economical cost separate compared to a well-established current meter. Currently, Nixon string flow 430 selling price is around 2,080 ringgit Malaysia. If the selling price of Nixon string flow is 3 times from its total cost, then the proposed current meter is expected to be 44.95 lower than the commercial current meter. So table 3 shows the analysis detail between the standard and the test meter of propeller type current meter. When the indicator reading was 44 Hz, the percentage error was 7.5 error. This indicates that the prototype meter cannot measure water velocity less than 0.5 meter per second. The percentage error will reduce and more precise when higher velocity of flowing water. The graph was plotted and shown in figure 5. The linearity of R squared is about 0.9625 for a standard propeller type meter value and the test meter, which indicate measured value produced by the test meter agreed with the reference water velocity measured by the standard meter. And the relative error of the prototype current meter can be reduced by inserting 1.009 for correction factor at the programming stage shown in figure 2. If the correction factor was applied, the systematic error of the test demonstrated should be less than 1% of inaccuracies shown in table 4. As a conclusion, the prototype current meter with electromagnetic measuring technique was a practical solution for a flow velocity measurement in the open channel. The prototype was calibrated in 8-meter-long flow channel that varied from 0.3 to 0.6 meter per second. The propeller type current meter responds instantly and consistently to any change in water velocity shown in figure 5. The desired velocity component was accurately registered with average error of 1%, which is an acceptable error. Additionally, the cost of meter was 44.95% lower than the commercial current meter. In the example is the Nixon Streamflow 430. A suggested future improvement is that the propeller current meter should be operated for a longer period of time to detect the occurrence of any system failure. Last but not least, the references. Here is the list of references used in this study. Thank you.